Today, we're going to talk about IR gas detection, specifically in terms of flammable gas detection. Thank you again for joining the session today. It's been a couple of weeks in prep for this webinar. I'm really excited. We're all very excited. Guess we got a few more people joining in. Moving on. For those who don't know me, my name is Yasin, and I'm the fixed product manager here at Crowcon. I'm based in the HQ of Crowcon in Oxford, UK. And just a bit of breakdown on what to expect. What am I going to talk about? So it's just importance of flammable gas detection, IR detectors, so different types of detectors, different detection technologies, operating conditions, challenging operating conditions, be it hot, humid, cold conditions, and what are the effects of those conditions on gas detection at your site, and a bit more regarding what have we done here at Crowcon to kind of improve detection technologies and what we on our products. A bit regarding power supply issues on products, on gas detectors specifically, and applications. So Crowcon was established in 1970. We got a brilliant team working behind the scenes to get the products that you buy from Crowcon a reality. We are really proud about the fact that we can deliver products to you on an average of 10 days lead time. I don't think there's any other company out there that can do that. I mean, by company, I mean gas detection manufacturers. Got a raging 98% customer satisfaction rate, again, making the impossible possible. Crowcon is a part of a larger company called Halma PLC. It's a group of 50 companies, probably more. But yeah, that it's part of that big company, along with other companies in the group. All the products that you might see on our website and the products that you order from Crowcon are manufactured and assembled on the same facility that I'm at, on the manufacturing floor that is specialized to build gas detectors, and that's all we do: manufacture, assemble, design, and produce gas detectors. We are trusted by different names out in the world. So you've got Tata, Unilever, Saudi Aramco, Petronas, and so on, ADNOC. Name all the big names. It's all there. We've got our products in all of those sites. So just to make this a bit more interesting and engaging, and just so that you don't have to keep listening to me ramble on about gas detection and flammable gases and IR and stuff, just thought it'd be a good idea to make it a bit more engaging. So you will now see a poll pop up on your screen. Select the industry where you primarily work in, or what sort of background do you come from, or which sort of customers do you primarily work with. And if you submit it, I can then talk about what the results are, what does it look like, and also tailor my content based on the results. I'll give that a minute, and then we can close the poll and move on to remaining of the presentation. The other thing I want to mention before I forget is, if you have any questions while I'm going through the presentation, feel free to add them onto the Q&A section or the tab on Teams. So then towards the end of this session, we'll have a Q&A session, and then I can start answering some of those questions that you have. All right, let's see. Let's look at the poll results. Right. So we've got 28% in oil and gas, 12% in power and energy sector, 8% food and beverages, 8% in chemical petrochem, 8% marine, 12% water, and 24% in from other industry. That's very interesting. So regardless which industry or background you come from, detecting flammable gases is without a doubt quite important, and that is to obviously protect your personnel and assets on site, make sure you're compliant with the safety regulations and requirements of your company and the policy, and obviously whatever product or feed product that you get on your site, it shouldn't just be exposed to the environment and you lose some of your production efficiency. And there are different ways in which you can detect flammable gases. And as you can see on the screen, there's catalytic bead sensor, MOS sensor, thermal conductivity, MEMS, laser sensors. But today we're going to focus on IR detection and IR sensor capabilities, what we can do and what sort of products you can work with. Generally, IR sensor, you'll find two types of IR detectors in the market. I'm saying generally. Is the first one would be a standard gas detectors with a capability of having different sensor options in them, and that construction of that detector is generally in a flame-proof enclosure, and you'll have a sinter behind which you'll have the IR sensor installed. And then you have the advanced flame-proof IR detector, in which case the IR sensing optics is embedded into the design of the product, which means you don't have any sort of removable sensor built into the detector, but the detector itself is an IR sensor, if that makes sense. And the biggest difference I want to highlight is that for gases to get to the sensor in the standard flame-proof enclosure, it has to pass through a sinter, whereas on the advanced flame-proof IR detector, the gases can pass through an unrestricted areas within the weather cap and go into the detection chamber. And that brings us to the second poll of the day, which is what from the two detectors I just described, what do you use if you got IR detectors on your site? What do you use? Is it the standard one? Is it the advanced flame-proof IR detector? Or is it both, depending on what gases and application you use it for? Or neither of them, you just have catalytic MEMS or other sensor types on your site. Or you don't have any flammable gases on site. So whichever applies, I'll just give it a couple more seconds and we can look at the results. All right, we've got 18 responses and it says 46% of response is leaning towards standard flame-proof gas, 8% only advanced IR detectors, and 38% said both, depending on applications. 8% says other sensor technologies, so which is interesting. And the reason why I thought this would be a relevant question is just to gauge on the understanding of what are the differences between the two, and what can you use the two detectors in terms of applications. And we'll talk about that in a bit. What are the differences between them? But the first main difference is how the sensor is designed or how the sensor is constructed. On the standard IR detector, you have a sensor module that looks like this, and you obviously have the IR source or lamp, which emits IR waves in different wavelengths, and you've got a mirror of which the IR waves bounces back onto the sensor. The sensor has a filter that filters out a certain wavelengths of the source, and the flammable gases absorb some of that IR waves, and the difference between what's emitted and what's received is kind of forms the basis on which a gas reading is given out by the detector. So that's like the kind of simplifying how it works. There are obviously a bit more complexity to it, but generally that's how it is. Moving on to the advanced IR detector, there are some differences in how they are designed. First of all, it must be obvious that the sensor module is expanded into the head of the detector and the tail of the detector. Similar way, the sensor and the source and the windows are constructed in a very similar fashion, but it's just separated out with a detection chamber in between. And the source emits IR light and comes back off the mirror, and the IR sensor absorbs some of that, and the gas absorbs some of the IR, and the sensor detects a difference. But then the biggest difference you would see here between the other sensor module is that you have a heater built onto the mirror, and you have a multispectral IR sensor instead of a single wave IR sensor. Apart from that, everything pretty much looks similar. You obviously have a bigger detection chamber, I would say. Brings us to the third poll of the day. What kind of flammable gases do you deal with on your site on a regular basis, or what's the most prominent one? You can select multiple options if you have many flammable gases on site. Give it a couple of more seconds. If there are any flammable gases that you deal with that are not listed here, you can just go for the other flammable gas option, because the ones that we focused on here are the most common ones that we generally deal with, but there might be other gases. All right. I think, all right, just got the results in. So you got 20% said hydrogen, 27% on methane, 13% propane, 11% butane, 10% said other flammable gases. We do have 6% benzene, which is quite interesting. I wasn't expecting a lot of response on benzene, but I'll touch up on that in the next slide. But first things first, you cannot detect hydrogen and acetylene with an IR sensor. I think that's fairly common knowledge, but I just wanted to highlight it again. If you have hydrogen on your site, you should definitely consider catalytic sensor or MEM sensor like MPS that we offer on our range. I'm not going to go into details of the difference between these sensor, but just IR sensor can't do it. You got ammonia and carbon monoxide. They weren't listed because I would consider them to be a toxic gas more than a flammable gas, although they are flammable gases. They just reach a much higher level of toxicity before it even gets to a flammable level. And that's why you should consider electrochemical sensors for those to detect ammonia and carbon monoxide. Now, benzene is a special case, similar to ammonia and carbon monoxide. Benzene is a flammable gas, but benzene is also a very toxic gas. I think the exposure limit is 2 ppm or something, compared to carbon monoxide, which is 50 or 100 or something. And that's why if you have benzene on your site, do not rely on flammable gas detectors to detect them. Go for a PID sensor, which can detect these gases in very low concentrations. Moving on, this slide shows the major differences between the standard IR detector and advanced IR detector. So obviously, I think this would be the first thing that would come into your notice, is that you got a very small surface area through which gases can pass through in a standard detector, whereas you have a lot of surface area, which is, just look at the size of the weather cap and the surface area of the weather cap, through which gas can pass in through and into the detection chamber. You only have one direction in which the gas can get into the sensor module in the standard detector, whereas on the advanced detector you have multiple directions in which the gas can get into the detection chamber. Now, because the surface area is so small on a standard detector, it is more prone to blockages, and that is not just to do with the surface area, but also how dense the sinter is. Most definitely, the sinter has a specified porosity and pore size, but it still is prone to blockages from dust accumulating on it, or even water or oil splashing on it and then dust getting covered. And that's why it's important. You might have noticed that the frequency at which you test a standard detector is more shorter compared to an advanced IR detector, where you might be able to push your frequency of testing it to like a year or 6 months, or sometimes even longer, depending on what your policy is and what your local regulations are. And leading on from the same point, now because the sinter has limited pore size, heavy flammable gases like hexane, due to its molecular size and how the bonds are between the molecules in hexane, the flow of hexane is impeded by the sinter. I'm not saying it will not pass through, but it will restrict the flow of hexane through the sinter, which makes it not an effective way to accurately detect hexane, the standard detector with the sinter. Whereas because there's zero resistance and the gas path is relatively open and unrestricted on advanced detectors, you should be relying on an advanced IR detector to detect heavy flammable gases. And there are few more subtle differences, like how the temperature range is higher on an advanced detector. Like you got -40 to 70 degrees Celsius temperature range and a humidity range of 0 to 100, whereas it's slightly lower on a standard detector, just because how they're constructed and how they operate, and limitations on the sensor module performance. You got slow response compared to an advanced detector on a standard detector, just because, again, going back to the sinter, kind of restricting the flow. Now, for light gases, the response time difference would be negligible. You could say that they're almost the same, but the heavier the gas is, the slower the response would be in the presence of a sinter. You also don't have a heater element on the standard detector, just because the humid air or wet air does not creep into the detection chamber in the sensor module, whereas it's easier, just because the gas path or air path is just unrestricted, it's easier for wet air to get in and form condensation on the mirror. And we'll talk about that in details following a couple of slides. The other thing I want to highlight is, as you can see in the picture, the standard detectors are supposed to be installed vertically, and the advanced detector are supposed to be installed horizontally, just to avoid water accumulation on the mirror, because that's the mirror sits right at the edge of that at the weather cap. Moving on, I'm sure a lot of you might face some of these extreme environmental conditions on a regular basis, or depending on what season you're in, or during what time of the day you're in. So it's like mornings, you have condensation problems. If you see water droplets on your windows, your car, or the grass, around you, that I'm sure that's a problem on your site. If you have wet and rainy conditions, or hot and humid conditions, or even freezing, some of you might have issues with those in terms of instrumentation on site. Now, that brings us to the next poll, where we just want to see how many of you have issues in some or all of these issues. It can't be all of this because there's like high temperature and low temperature, but it'd be interesting to know what that looks like from everyone online. So you should get the poll up on your screen in a second. There you go. And I'll leave it open for a minute, and then we can go through results. I see that there's a couple of questions on the Q&A tab already. Feel free, if there's any questions that you think about during the slides, feel free to put them up on the Q&A tab. I'll be answering a lot of those questions towards the end of the session. So hopefully, if I can get there, finish this off in the next 20 minutes, then we have plenty of time to go through question and answers. All right. So we got some of the results back here. So 20%. So the highest one is high temperature. So 24% people said they deal with 40 degrees Celsius and above on their site, 20% on high dust, 12% high rain, 16% high humidity, which is 90% and above, and liquid splashes, that sits at 16%. All right, interesting. Actually, I'm surprised by the number of low temperature, which is only 6%, but that's okay. That's good. So following through with some of these conditions, and let's break it down into what are the effects of some of these extreme temperatures on gas readings. And for that, I would just like to illustrate it with a simple graph. Obviously, this is it's obviously more complex in a minute detail level, but this is just how it represents. If you've got 50% LEL gas being exposed to an IR gas detector, and I stress on the IR sensor because different sensors behave differently in different conditions, but specifically for IR sensors, just because we go through a process of linearization, the detector tends to underread at lower temperatures and overread at higher temperatures. So if you have 50% LEL methane at minus 40 degrees Celsius, the detector would give you a reading of 45% LEL instead of 50. And that's just an example. It's not exact numbers, but it's just a representation of how it works. And at 70 degrees, at very high temperatures, you apply 50% LEL, you would get reading of 55%. In which case, it's a safer region at higher temperature because the detector is overreading. So you get to an alarm level faster. That's fine. It's the negative side, is the lower temperature side, should be careful about. And that linearity, or the how much it deviates from what they expect in terms of reading, gets worse with some gases, and this is just an example of how it looks. Similarly, for humidity, the curve is quite the opposite. So at very low humidity levels, the detector tends to overread, and at high humidity levels, the detector tends to underread. So again, the risk, the riskiest side is on a higher humidity level. But I do want to highlight the fact that the deviation on humidity is much, much, much lower compared to deviation from temperature range. I hope that's clear. If there's any questions, please send it my way, and I'll be happy to explain further. So as part of every gas detector manufacturer goes through a series of tests to make sure the products are doing what it's supposed to do and is as close to the reading as it's supposed to be. And one of the tests that we do at Crowcon as part of the certification process is humidity testing, which means we put the detectors in an environmental chamber and keep the temperature constant to avoid condensation being formed on the detector, and raise the humidity levels from 20 to 50 and 90 to make sure the detector doesn't go into fault, it's stable, and so on. Similarly, a temperature test is also done where the humidity is kept constant so that there's no condensation happening, and the temperature is it goes from a low value to a high value, again, just to avoid condensation from happening in the chamber. And that goes from minus 20 to 55 or minus 20 to 70 and so on. And that kind of essentially forms a part of the performance certification. So if you see a IEC 6007929-1 or an FM 6320 or even an EN 6007929-1, all of these are essentially very similar performance standard for flammable gas detectors, where a third party, a certification organization or a test body, will take samples of detectors and test them through temperature, humidity, response time, vibration, and multiple other tests, and make sure the detector does what it's supposed to, and it detects gases in different conditions. And the stuff you see on the left-hand side is actually part of that test. It's specified in these conditions. So you test the detector at 40 degrees and cycle through different humidity levels and keep the humidity constant and cycle through minus 20 to 55. And that's the standard mentioned in these certification process. But at Crowcon, we do a bit more. So to kind of simulate real life conditions where you would have condensation issues. You would have condensates forming on the detector in the process area, and see these droplets of water just trickling down the detector. And just to simulate that, what we did was we put an IR plus, in this case IR plus, for example, in a chamber where we forced condensation to happen by introducing humid air into the chamber and increasing the temperature, and make sure it doesn't go into fault. And this kind of makes it more suitable, IR plus, more suitable for wet applications or humid areas in which condensation is a problem. And that is possible due to a couple of things that we do at Crowcon. But one of the things that we do is put IR Plus through a dynamic environmental learn process. And by that, I mean IR Plus is put into a chamber that runs for 24 hours, cycling through different temperature levels across all across the 24 hours time. And that pretty much makes the electronics learn what is supposed to be the output reading from the gases, and at different temperatures, starts at minus 40, goes all the way to 80 degrees Celsius. And so that makes it the detector kind of learn through the whole temperature curve without us programming the same thing into the electronics. And that's kind of makes every single IR Plus unique in some sort of way. And the other thing that we do is the same electronics kind of does a heater map that during the learn process. So essentially, when you have a mirror without a heater on it, and if you are in one of those areas where there's condensation issues, water droplets or mist kind of blocks out the mirror, which impedes or which obscures the mirror, and you will have an obscuration fault due to that, which you don't want to have during your normal operation. But with a heated mirror, what you'll see is that the condensation, even if it forms and sticks to the mirror, the heater pretty much evaporates all of that water molecules from the mirror surface and maintains a clean area on the mirror surface to make sure you have 100% no fault conditions. And what we've done is to make sure the heater element as well has some sort of input on what level of power it's supposed to output. So you've got a temperature sensor inside the detector that looks at ambient temperature. And if the temperature is high enough, the heater starts to taper down in terms of how much percentage it outputs. So you'll have 100% at 20 degrees, for example, to make sure the condensation is evaporated. But if the ambient temperature goes beyond 40 or 50, then it starts tapering down. And we've done that through the learn process. But why did we do that is the next part of the presentation. Just so that you know, the heat electronics and the heat element sits right behind the mirror there, which probably can't see the mirror, but that's pretty much in the end side of it. And that leads us to the next question on power supply issues. Now, this is not very common, but we do come across a lot of our customers coming back to us saying we've had voltage drop issues, or we purchased a detector, but then with a certain power consumption, but then during startup, it was drawing much more power or current for the first 10 minutes. And because of that, the power supply design was insufficient and so on. So you should have gotten the poll up on your screen. If you've had any of these issues, put that in, but if not, just go for the no issues option. All right, so 14% said no issues. 24% said voltage drops. 24% said long cables, long cable lengths causing signal losses. 14% said insufficient power supply, 14% said high inrush current. So it's fairly quite well distributed response on that. Interesting. Thank you for your responses. I'm just going to try to touch on some of those topics in the next few slides. So generally, when you have a gas detector that you're looking at in terms when you're going through a design stage, when you're mapping out your site, you're deciding how many detectors you want, and you get the number of detectors and say, I'm going to choose this detector. You look at the data sheet, and most likely you're going to see a nominal power rating on the data sheet. And that's generally lower than the maximum power the detector consumes. And the difference comes in, especially during startup. So when you have a detector that's not powered up, you hook it onto the power supply system and you power them on for the first couple of minutes. The detector, because of the electronics powering up and the heater warming up and the sensor warming up, it consumes slightly more power than the nominal power consumption. During normal operation, once everything is set up, it should come back to it. But that's how it is. And you design a system that way. And let's say you go for a slightly higher, just for FYI, the numbers here are just representative. So you go for a power supply higher than what it's supposed to do. But when you start up, because the power consumption at startup is higher than your design power, you go into a fault. And then it gets worse when you have 2 or 3 or hundreds of detectors on your site. That difference kind of comes in and gets you into issues on power supply. But in regular normal operation, you're still okay because you designed it for the normal power consumption and you keep using it. And some of you might have mentioned about long cable lengths causing signal losses. Again, that is to do with the loop resistance when you calculate the loop resistance and take that part into consideration. Without having to go into too much detail. But again, if there's anything like that we can help with, helping you design system, please feel free to reach out to us. I'm sure we have our team be happy to support you. Now, one of the things I want to highlight from a product that we have in our range is IR Plus, and the highest or maximum power consumption from IR Plus, if you switch on the heater is going at 100%, the electronics are online. You got a reading of 24 milliamp. You got a display working on it. Everything operational, the maximum power consumption will be under 5.5 watt. And if you remember me talking about the intelligent electronics, that what pretty much contributes to that efficiency in power consumption. So we've made sure every part of the detector uses just enough power to do what it's supposed to do, but then without compromising on performance. And I want to highlight that out of this 5.5 watt, 80% of the power is consumed by the heat. And that's why it was so important to actually map out how the power is consumed by the heater. You don't want the heater to be working at 100% 24/7 unless it's necessary. And bear in mind, there are some detectors out there in the market that consumes up to 13 watt of power in certain conditions. And there could be reasons why there's voltage drops or high consumption over longer cable lengths, and it's just about awareness and selecting what you need on your site. That brings us to a general question about what applications do you use your IR detectors for? And I'll talk about why this question has come up. Is it just for environmental monitoring purposes? You just want to monitor methane emissions into air, or is it because you want is it for safety monitoring where you want to make sure you know about a gas leak to protect your personnel and assets, or is it to perform an automated procedure where you shut down a valve or shut down the process area and so on, with different inputs being voted as input. Sorry. You should have received that poll by now. But if you don't know exactly what the application is, feel free to go with I don't know, and then we can go through the different options. Give that a couple more seconds. Oh, we've got the results back in. So 15% said environmental monitoring, 44% said safety monitoring, and 41% said emergency shutdown or safety systems. So again, this is just highlighting the fact that for environmental monitoring, you don't really care much about response time or how quickly you get the data from the detector, or how quickly your control panels have to act, or you don't worry about the consequences in short term. You obviously look about reporting the emissions, and you try to fix that over, like, let's say the next 3 months or 4 months over during your next shutdown. But you don't care if the data comes in 2 seconds or 10 seconds later. As long as the data is there, you're able to access them and log them. For safety applications, on the other hand, you want the detector to give you an alarm as soon as possible, in the fastest time, 4 to 5 seconds, because it's safety critical. You don't want the detector to be offline or in fault when a gas leaks, or there's some sort of gas leak on your site. So imagine a detector online, it goes offline for a day or an hour, and that's exactly when a gas leak happens, and that kind of puts your site at jeopardy, or you have an unsafe condition there. And ideally, it should be performance tested, because you want to know the detector that is coming on your site has actually gone through comprehensive testing, so that regardless of what conditions your site is at, your gas detector is working properly. And finally, for safety critical applications or shutdown applications, you want to go even further to make sure the detectors are evaluated for functional safety, and you know that the detector is only going to fail in detectable failure modes. So it's worth understanding the failure modes of the detector. So if you have an instrument that would fail and you will never get a fault alarm, that's the most dangerous way of having a failure on site. If it's a detectable failure, that's fine, as long as you're aware and you have backup in place. You have a portable detector in place there to make sure you're covered and you're safe. That's a more controlled and detectable failure mode, and that's why SIL rating on products are important. Generally, you have gas detectors with SIL 2 or SIL 3 performance rating, and that just ensures or gives you a peace of mind when it comes to automated systems. And that brings us to highlighting a product that was recently launched at Crowcon, which is IR Plus. So everything that we have spoken about earlier, be it extreme conditions, environmental conditions, long life, product life, low power consumption, performance testing, SIL 2, downtime. So it's like different features on IR Plus that makes it minimizes downtime on the product, and other features on the product. Just want to highlight that. And if you want to read more about the product, you can access our product page on www.crowcon.com, or reach out to us if you have any questions on the product. And that brings us to the end of the session. But if you have going to start looking at questions, feel free to add any questions that you may have onto the Q&A tab now, and I can just start answering some of them. All right. I only see 2 questions so far. I'm not sure if there's any other one. So I've got one question that says, any specific detectors for methanol in ppm range and percent LEL? I'll have to look at the flammability level of methanol, but we do have methanol gas detectors. And although IR Plus is a flammability detector, we haven't done a linearization on methanol for IR Plus. And but then it's something that could possibly happen down the line in the future. All right. I don't see too many questions. So I guess if you have anything else or any other questions, feel free to send it our way using the contact form or the emails that we provided earlier. And we'd be happy to get back to you with some of the answers. I would like to say that all of you would get a copy of the presentation slides, and we will have a white paper that is expected to be released towards in the coming weeks. So thank you again for joining us today. It's been a pleasure talking to you. Hopefully that was informational and you learned something from me. If there's any, if you can take a minute to fill out the last poll, which is about feedback. How did you find the webinar? If there's any content you'd like us to talk about in the coming future. Is there any subject you wanna get more insight into, that sort of thing? If there's anything like that, please fill it into the feedback poll. We'd be happy to look at it and just come back to you guys with another session soon enough. Thank you, everyone. Hopefully you enjoyed it. I'll see you guys soon. Have a nice day. Thank you.